In this video, we will discuss about the maximum power transfer theorem for a complex load or a load that has a reactive component, which means that this load ZL here can have resistance and an additional either inductive or a capacitive load. And this source is driven by a voltage source Vs here, and again the source impedance can be resistive plus another inductive or a capacitive component, which will translate into a component which we denote by Xs into J. So ZL is represented by RL plus Xj, and source impedance is represented by R source plus X source into J, and it is driven by a V source. The V source and this Zs component is fixed, and we are trying to vary this ZL component, RL and XL, and we are trying to find out for what value of ZL the power delivered to this will be maximum. This theorem has very important implication. If you have not seen, if you do not know the basics of the maximum power theorem for a simple resistive network, you can check my video about it. I hope you understand that if these are purely resistances, then we know that if RL is equal to RS, the power delivered is maximum. We want to extend this theorem for these reactive components. The method is same. The theorem has very important implications, for example, antenna theory, impedance matching, and so on and so forth. For example, the load here could be something like that, 50 plus 70J, for example, if we have an inductive load, or could be 40 minus 21J with some resistive component of the load. And the same way, the source impedance can also be something like 40 plus 70J or anything. It can be anything. So once we know this power transfer theorem, I will have some more lectures on the impedance matching thing. But if you want to understand this maximum power theorem, will form the basis of these impedance matching circuits that we will look into later on. So for this resistance, let's apply the Kirchhoff voltage law, and from the Kirchhoff voltage law we get I as a vector quantity or a phasor as Vs divided by this component Zs plus ZL. I have not done anything special here, just apply the Kirchhoff voltage law and I get this component of this current flowing. And this current will be flowing, which I show it with this arrow, is going to be same in this resistor, the source resistor, as well as the load resistor. Now we know that the current flowing in this one, then what we mean by the power transfer is the average power, not an instantaneous power. We are taking cycle after cycle and we are averaging the whole power that goes into this load, and that power P average will be equal to, or can simply call it P load, will be equal to I RMS square divided by this load resistor Z I square into ZL. Now, since we are taking the average power on the load, that is cycle after cycle, and take the average, this load resistor has two components, RL and XLJ. What happens is the power is consumed only in RL. The power is delivered only into RL. In the XL, the instantaneous power may have some value, but if you take it cycle after cycle, it zeroes out. Its average value is 0. What it means is that, let's say we have a resistor and a capacitor, and you drive it, let's say, through the sinusoidal waveform. Then in half the cycle the capacitor gets charged, and the other half the capacitor discharges the current through this resistor. So whatever energy is stored in this capacitor is given back in the other part of the cycle. But In the resistor, whatever power delivered is lost either as a heat or as a radiation or whatever else. So this power IRMS square multiplied by ZL will be same as IRMS square multiplied by RL. And the next thing that we say is that the RMS value of this I will be equal to I square divided by 2. We know that the RMS value is half the peak value or half the value of this current I or the phasor I. And on I square we can write it as, we can also write it as mod of Vs square divided by, we can also write it as mod of I square. IRMS square is actually the mod of I squared divided by mod of Zs plus mod of Zl whole square multiplied by RL. The I here is actually a phasor with the components of x and y axis written, but eventually the power is, the average power does not have a vector, and that's how we are going to represent it. Now Zs plus Zl mod whole square is nothing but, if you want you can apply the formula here. For example, Zs is equal to Rs plus Xs into J, and ZL is equal to RL plus XL into J, and Zs plus Zs, if you write Zs plus Zl vector, that will be Rs plus RL plus XS plus XL into J, and if you take the modulus of this, then it will be square root of Rs plus RL whole square plus XL plus XJ whole square. We can also find this modulus using taking the dot component of Zs plus Zl and Zs minus Zl. It's a complex numbers formula. I will not go into the math of it, but I will write the final result. Vs mod whole square multiplied by RL divided by Rs plus RL whole square plus XL plus XS or XS plus XL whole square. Our purpose is to maximize the power to this load. And how we can maximize it? To maximize this, we need to minimize this term. And this term has two square terms, RL plus RL, Rs plus RL whole square and XS plus XL whole square, which means that these two terms must be individually minimized, which means that this term has to be minimum and this term has to be minimum. For this term, XS and XL, there is a clue or a possibility that they can have different positive and negative direction. That means by choosing the XL such that it is minus XL, we have one condition that PL will be maximized. So for PL to be max, I have number one condition, XS plus XL is equal to 0, which also means that the load impedance must be the complex conjugate of the XS. That is this is a very important deduction, something that we will be using over and over again and again in impedance matching, in antenna circuit and all the RF circuits and at many other places. What does that mean? Let us say you are given a source resistance of 40 plus, let us say 70J, and you have a choice to choose this load resistance to maximize the power delivery. What you are going to choose? This has to be like minus 70J. We will come back to RF. Let us say I have this thing as 60 plus minus 3J. What does that mean? We should choose load such that is this component, XL component, has to be plus 3J. How can we possibly have 70J? 70J means this has a net inductive component into this. XL is equal to 2 pi F into L, and which means that this one, so this one is something like a net inductive component, which means that if this one has an inductive component, this one should have a net capacitive component like this. This is because the capacitive component is given by 1 upon 2 pi F into C, or J times minus times J, and J goes up, becomes minus J. So this is something we need to keep in mind. So coming back to that, once we have XS plus XL set to 0, we have the power is equal to Vs squared multiplied by RL divided by Rs plus RL whole thing squared. And we have seen earlier that this whole thing, for PL to be maximum, we should have Rs plus RL whole square divided by RL should be minimum, and that happens when RL is equal to Rs, which means that we need to do two things for the load for the maximum power delivery. Number one, we need to set its complex conjugate for the reactive term, and then we need RL exactly same as Rs. So this is whole about the maximum power transfer theorem. We will be doing again and again. It's the basis of the Smith chart, impedance matching thing, and many other things. We will discuss these things in the video. I will try to make next video about the impedance matching. If you are interested, check that on.